quick physics tutorial.
Hello everyone. In this video, we will have some examples of quantum mechanics, particularly blackbody radiation, photoelectric effect, Compton effect, de Broglie wavelength, and uncertainty principle. Problem number 1. The average threshold of scotopic vision is 4.00 times 10 to the negative 11 watts per square meter, at a central wavelength of 500 nanometers. If light with this intensity and wavelength enters the eye, and the pupil is open to a diameter of 7.00 millimeters, compute how many photons per second enter the eye. Let us write the given values in the problem. First, we have the intensity of a scotopic vision, expressed as power over area, which is equal to 4.00 times 10 to the negative 11 watts per square meter. Then its central wavelength is 500 nanometers, or equivalent to 500 times 10 to the negative 9 meters. Also, the diameter of a pupil is 7.00 millimeters, or equivalent to 7.00 times 10 to the negative 3 meters. The radius is just 1/2 of the diameter, so the radius is 3.50 millimeters, or equivalent to 3.50 times 10 to the negative 3 meters. The problem is asking for the number of photons per second entering the eye. The number of photons required to yield this energy is n equal to E over E lambda, where E is the energy entering the eye per second, and E lambda is the energy of a single 500 nanometer photon. The energy E entering the eye per second is expressed as P times delta T, where P is the power, and delta T is the period of the light entering the eye. Since intensity is power over area, P is I times A. This area is the area of the pupil, which is just pi times the square of its radius. So we write the energy E entering the eye per second as I times A times delta T. Plugging in, we have 4.00 times 10 to the negative 11 watts per square meter times pi times the square of 3.50 times 10 to the negative 3 meters times 1.00 second. We get 1.539 times 10 to the negative 15 joules. It's in joules, because 1 watt is equivalent to 1 joule per second. We cancel the units, second and meter, so we are left with joule. We can also write the energy as 1.54 times 10 to the negative 15 joules, since we have 3 significant digits from the plugged-in values. Next, the energy of a single 500 nanometer photon is expressed as hf, where h is Planck's constant, and f is the frequency of the photon. The frequency f is equivalent to c over lambda, where c is the speed of light, and lambda is the wavelength of the photon. So the energy of a single 500 nm photon is hc over lambda. Plugging in, we have 6.626 times 10 to the negative 34 joule second times 3.00 by 10 to the power of 8 meters per second over 500 times 10 to the negative 9 meters. We get 3.9756 times 10 to the negative 19 joules per photon. We can also write the energy as 3.98 times 10 to the negative 19 joules per photon, since we have the least significant digits of 3 from the plugged-in values. Going back to the number of photons required to yield this energy, we write N equal to E over E lambda. Plugging in, we have 1.54 times 10 to the negative 15 joules per second, divided by 3.98 times 10 to the negative 19 joules per photon. So the number of photons required to yield this energy is 3.87 times 10 to the power of 3 photons per second. Problem number 2. Electrons are ejected from a metallic surface with speeds of up to 4.60 times 10 to the power of 5 meters per second when light is used with a wavelength of 650 nanometers. What is the work function of the surface? And what is the cutoff frequency for this surface? Let us write the given values in the problem. First, we have the speed of the electrons, equal to 4.60 times 10 to the power of 5 meters per second. Then, we have the wavelength of light of 650 nanometers or 650 times 10 to the negative 9 meters. The problem is asking for the work function of the metal's surface and the cutoff frequency for this surface. We start with the expression of maximum kinetic energy of ejected electrons, which is energy E minus the work function phi. Rearranging the equation, we get the work function phi equal to energy E minus the maximum kinetic energy. So in this case, we will determine first the energy E and the maximum kinetic energy in order to solve for the work function phi. Energy E is expressed as hf or hc over lambda. Plugging in, we have 6.626 times 10 to the negative 34 joule-second times 3.00 by 10 to the power of 8 meters per second over 650 times 10 to the negative 9 meters. Cancelling the units, meter and second, and computing them, we get the energy E equal to 3.058 times 10 to the negative 19 joules. Converting it in terms of electron volt, we obtained 1.911 electron volt or 1.91 electron volt. Next, we solve for the maximum kinetic energy of ejected electrons. The maximum kinetic energy of ejected electrons is equal to 1/2 of the mass of electron, 9.11 times 10 to the negative 31 kilogram, times the square of its maximum speed, 4.60 by 10 to the power of 5 meters per second. Computing them, we get 9.64 times 10 to the negative 20 joule. Converting it in terms of electron volt, we obtain 0.6025 electron volt, or 0.603 electron volt. Going back to our equation of work function, 1.91 electron volt minus 0.603 electron volt, we obtained the work function of the metal's surface to be 1.31 electron volt. Now, we solve for the cutoff frequency for the metal's surface. For this one, we just use the expression of energy equal to hf. Take note that at the cutoff frequency, the energy of the photons is equal to the work function of the surface, equating hf and the work function phi. Rearranging the expression, we obtain the cutoff frequency equal to the work function phi over h. Plugging in, the cutoff frequency is 1.31 electron volt over 6.626 times 10 to the negative 34 joule-second times the conversion factor, 1.60 times 10 to the negative 19 joule in 1 electron volt. Cancelling the electron volts and joules, we are left with 1 over second or hertz. So the cutoff frequency is 3.163 by 10 to the power of 14 hertz, or 3.16 by 10 to the power of 14 hertz. Problem number 3. X-rays are scattered from a target at an angle of 45.0 degrees with the direction of the incident beam. Find the wavelength shift of the scattered X-rays. In this problem, the only given value is the angle theta of 45.0 degrees. The problem is asking for the wavelength shift of the scattered X-rays. From the Compton shift equation, we will just plug in the necessary values to solve for the wavelength shift. Planck's constant 6.626 times 10 to the negative 34 joule-second, over the mass of the electron, 9.11 times 10 to the negative 31 kilogram, times the speed of light, 3.00 by 10 to the power of 8 meters per second, times 1 minus cosine of 45.0 degrees. 1 joule is equivalent to 1 kilogram m squared over s squared. Cancelling the units, we are only left with meter. Computing them, we get 2.42 times 10 to the negative 12 meter, times 1, minus 0.707. We place the conversion factor of nanometer. 1 nanometer, equivalent to 10 to the negative 9 meter. The wavelength shift is now 2.42 times 10 to the negative 3 nanometer, times 0.293. So the wavelength shift of the scattered X-rays is 7.09 times 10 to the negative 4 nanometer. Problem number 4. Calculate the de Broglie wavelength of a proton, moving with a speed of 1.05 times 10 to the power of 6 meters per second. In this problem also, the only given value is the speed of the proton, equal to 1.05 times 10 to the power of 6 meters per second. The problem is asking for the de Broglie wavelength of the proton. For this one, we will use the de Broglie wavelength expression. Lambda, equal to Planck's constant h, over the momentum of the proton p, where p is mass times speed of the proton. Plugging in, we have h, 6.626 times 10 to the negative 34 joule-second, over m, 1.67 times 10 to the negative 27 joule-second, times u, 1.05 by 10 to the power of 6 meters per second. 1 joule is equivalent to 1 kilogram m squared over s squared. Cancelling the units, we are only left with meter. The wavelength is now 3.779 times 10 to the negative 13 meter. We place the conversion factor of nanometer. 1 nanometer, equivalent to 10 to the negative 9 meter. So the de Broglie wavelength of the proton is 3.779 times 10 to the negative 4 nanometer. Problem number 5. If the lifetime of a muon is about 3 microseconds, estimate the minimum uncertainty in the rest energy of a muon. In this problem, the only given value is the lifetime of a muon, about 3 microseconds. The problem is asking for the minimum uncertainty in the rest energy of a muon. In here, we use the Heisenberg uncertainty principle, delta E times delta T greater than or equal to h bar over 2, where h bar is just h over 2 pi. Rearranging the expression, we get the minimum delta E equal to h over 4 pi delta t. Plugging in, we have h, 6.626 times 10 to the negative 34 joule-second, over 4 pi, times delta t, 3 times 10 to the negative 6 second. Cancelling the units, we are only left with joule. Computing them, we get 1.7576 times 10 to the negative 29 joule, or 1.758 times 10 to the negative 29 joule. So the minimum uncertainty one can have in the measurement of a muon's energy is 1.758 times 10 to the negative 29 joule, or 1.10 times 10 to the negative 10 electron volt. And that's it for now. We hope that you have learned something in this video. Thank you for watching.